this video, I am talking about chapter number 14, Electromagnetism Part 3. Force on a moving charge in a magnetic field. We have seen that a current carrying conductor, when placed in a magnetic field, experience a force. The current through the conductor is because of the motion of the charge. Actually, the magnetic field exerts force on these moving charges, due to which the conductor experience force. We are interested in calculating the force exerted on the moving charges. Consider the situation as shown, where we see a portion of the wire that is carrying as current I. Suppose there are n charges carried per unit volume of the wire, and that each is moving with the velocity v. We will now find how long it takes for all the charge carries originally in the wire segment shown to exit through the end area A. The volume of the wire segment is AL because there are n charge carries per unit volume. The number of charge carries in the segment is NaL. If the charge on a charge carries is Q, each of it is as it crosses the end area will transport a charge through it, assuming the speed of the carriers to be v. The carriers and entering the left face of the segment takes time delta t equal to L over v to reach the right hand face. During this time, all the charge carriers originally in the segment, namely NaL, will exit through the right hand face, as each charge carries has charge q. The charge delta q that exists through the end area in the time delta t equal to L over v is. It can be seen that the direction of the segment L is the same as the direction of the velocity of the charge carries. If L is a unit vector along the direction of the segment L and V are unit vector along the velocity vector v, then thus the force experienced by a single charge carriers moving with velocity v in magnetic field of strength b. Although v in the equation has been derived with reference to the charge carriers moving in a conductor, but it does not move any parameter of the conductor, so the equation is quite general and it holds if for any charge carriers moving in the magnetic field. If an electron is projected in a magnetic field which is velocity v, will be experienced a force which is given by putting q equal to minus e in equation where e is the magnitude of the electromagnetic charge. Note that in case of proton or positive charge, the direction of the force is given by the direction of the velocity v cross b. Rotation and curl the fingers of right hand in the direction of the rotation. Thumb will point in the direction of the force. This is illustrated in which the proton enters into a magnetic field along the direction of the dotted line. It experiences a force in the upward direction as given by the vector v cross b. As a result of this force, the proton is deflected upward. The direction of the force on a moving negative charge will be opposite to that of force moving a negative charge will be opposite to that of positive charge. Due to this force, the electron is deflected in the downward direction as it enters into a magnetic field. It may be noted that the magnitude of the force on the moving charge carriers QVB sin theta, where theta is the angle between the velocity of the carriers and the magnetic field. It is maximum when theta is equal to 90 degree, when the charge particle is projected at right angle to the field. It is zero when theta equal to 0 degree. A charged particle projected in the direction of the field experiences on no force. Motion of charged particles in an electric and magnetic field. When an electric charge Q is placed in the magnetic field, it is experience a force if F parallel to electric field. If the charge is free to move, then it will be accelerated according to Newton's second law. As if electric field is uniform, then acceleration is also uniform, and hence the position of the particle at any instant of time can be found by using equations of in uniformly acceleration motion. When a charged particle Q is moving with velocity v in a region where there is an electric field E equal to magnetic field B, the total force F is the vector sum of the electric force QE and magnetic force equal to QV cross B. This force is known as Lorentz force. It is to be pointed out that only the electric force does work while no work is done by the magnetic force, which is simply a deflecting force. Okay guys, thanks for watching this video. Subscribe my channel and like this video. Bye guys.